Talk about XML. We have taken a look at a couple of ways that we can share data with non-users. At the very beginning, we were interacting with our database through the console, either with MySQL Workbench or either at the command line with MySQL, and then we started looking at other alternatives of how to interact with the database. We took a look at interacting with Java, JDBC, and every time we took a look at how to interact, we created a layer of abstraction, right? First, obviously the database itself is a layer of abstraction, right, over some binary representation on the file system. There are no real tables, right? We just have a conceptual understanding of how is it we think about the data, right? And that is the abstraction that we chose as a means of understanding about the structure of the data. We created a layer of abstraction on top of that, which was JDBC, which allows it to represent and interact with the data using connections, SQL statements, result sets, and whatnot. We created an even larger abstraction on top of that, and through JPA that allows us to think about the database not in terms of tables and foreign keys and primary keys, but instead in the object world, right? And we let then a middle tier decide how is that mapping should occur, right? Through using an ORM implementation. In this particular case, we took a look at JPA. We then moved a little bit towards other ways of representing data. We looked at JSON, driven by the popularity of web applications, and it turns out to be now the #1 way of that data is being shuttled back and forth between multiple processes. But before there was JSON, there was XML. So XML became very, very popular, in the late 90s, where multiple competitors were looking for mechanisms of an easy way of sharing data amongst multiple endpoints, right? And they had all these legacy database systems, that they've been using for decades of lots of information that have been storing for quite a bit. And they said, well, how can we expand the usability and the monetize on this large amounts of data sets that we've been collecting for quite a bit. And XML turned out to be one of the ways that these folks were, most of them agreed on how is it that the data can be easily represented, read by human beings. It's not a binary representation. Anybody can open up an XML document and edit it by hand. There was plenty of parsers, XML parsers out there that it was easily parsable and converted into an object representation. And it became the #1 way of shuttling data back and forth between endpoints, right? It was ASCII. It was just plain old text, right? It was not binary. It was easily shuttled across through the network. This also worked well with the choice of using just plain old HTTP as a mechanism, as an infrastructure for communicating between processes, as opposed to having processes open up a particular port to be able to communicate. The port 80 was already open, right? And nobody really cared about it. It was mostly used for entertainment purposes anyway. And so it was very easy to set up servers and for them to talk and just exchange XML in the process. So folks were looking for ways. Well, I have all this data stored in my relational database. I like to be able to represent it somehow in an XML format. And just like we looked at mechanisms for converting relational databases through JPA as JSON, well, before JSON there was ways of converting that same relational database into XML. Okay, but unlike the converting the Java or the relational database into JSON, there's a loss of information there a little bit, because JSON is still somewhat of a poor choice, right? Because there's no support for like a schema, right, of defining what the document structure should be, so that we can't really validate whether the document that we're receiving is valid, right? That the structure is correct. There are no really strong typing either, right? There's no way of describing that certain fields should be of a particular type. Whereas XML turns out to have been a better choice at some point, right? Where we do have strongly typed, we have structure, we can validate all these things. So in a sense, we've kind of regressed, going from something that was very, very strongly typed and structure and hierarchical, right? Going into an object representation, but perhaps of a little less less value. Okay, but nevertheless, XML is still plenty used today for configuration purposes and still data transfer. So let's look at and play around with XML. Yeah, so what we want to be able to do is expose the data and make it available to non-users who don't have direct access or even JDBC that might be able to make a network connection to your database, right? Instead we want to wrap all that into some kind of service, which we've done. We've wrapped it around JSON services. We can also wrap them around XML services as well. Obviously, it's not very useful that we might choose a poor representation of our data, such as maybe a line per record, and perhaps tabs or commas separated, or special characters that can be used to separate the values of particular records. Instead, we want something that is a little more powerful, and XML is certainly a good choice. So XML, as you might know, it stands for Extensible Markup Language. That it's a generic format that allows to add some context or some meaning to otherwise just plain text. So you might look at an address and using your frontal cortex, the way it's written, you might parse it as an address. We don't have that yet. Well, actually we do, but that could parse that and extract meaning from that raw text. XML allows us to formally, mark up the content and give some context. It says, hey, this is the first line, first address, and this is the city, and this is the zip code, and this is. It allows us to add meaning and context to the data, so that processes can parse, right, and extract the data from a very well formatted and marked up document. It's extensible, meaning that it can be used in any context. XML can be used to represent any type of information. You can represent mathematical formulas. The most famous and most common use of XML that most of us are familiar with is HTML, right? Web pages that allows us to mark up an ASCII document saying that this is a header, this is a paragraph, this is a line item, and whatnot. But before there was HTML, XML certainly had a much more broader use, and we've been using it, for instance, for configuring our projects in the POM files, pom.xml. But certainly it has a much more broader appeal than those limited uses. Also, it has a very powerful mechanism for describing what the structure of the documents are through what are called XML schemas. That you can describe that. Just like in a relational database, you create a schema using a table, right? Saying that these are the fields, and then you say the data types of those fields. Yes. So XML has an equivalent called schemas, and they themselves are written in XML, right? It's XML documents that describe another XML document, right? That says, hey, those documents over there are going to have these fields, and certain fields are going to be strings, and some fields are going to be dates, and some fields can be nested in other fields, so it can describe also the structure of the document, right, in the XML document. And then these schemas can then be used for validating a document. So if you get a document, you can then validate it against that schema and say, hey, is this document correct? Does it have the right data types? Is a hierarchical structure correct? Very much like if you have an object instance in memory, you want to validate that it matches a particular Java class, right? If it doesn't match, something went wrong. obviously, typically those instances were created from the Java class template. You generate a instance. So an XML schema is like a Java class. An XML document is like a Java object instance. Yes, and you can validate one against the other. Same thing in a relational database. A record is the equivalent of an XML document, but the table or the schema of the table is the equivalent of XML schema. Make sense? So here's an example of an XML document. It's you'll notice that it has lots of pointy brackets that describe what are referred to as elements. So we have here the enrollments element that contains several other elements. In this case, it contains 5 other elements all called course taken. And it looks like this has structure, right? That there's a root element and then several child elements, all the same type. Course taken. It looks like course taken. They all have the same attributes, student name, graduation year, year taken, grade, and whatnot. So it looks like they all have the same schema, right? They all have the attributes and whatnot. And also this represents the same examples that we've been looking at throughout the semester about students and courses and sections and whatnot, and how they are enrolled. But this is not the only representation. We could represent this data in a completely different way, right? We've chosen here that the courses are children of the enrollments elements. Well, we could have chosen a completely different representation for this data. But let's choose this for a bit. One of the things that you might want to point out here is that you'll notice that they all seem to have graduated the same year, 2009. Okay. Whenever you see repeating data like that, whether it's a field in a relational database or a field in a JSON object where you have many documents where you have those fields, you should always question yourself, right? So is this the best way that we can structure this, right? It looks like this value of 2009 seems a little bit redundant, right? That is being captured, many times, right? And we should always question whether this has been fully normalized or this is a denormalized representation, right? Again, we want to avoid at all costs redundancy because it might breed inconsistency, right? If for some reason this enrollments was for all the students that graduated in 2009, then certainly if that's the meaning of the graduation year here, and this is the response of some query of retrieve for me all the enrollments of 2009, certainly this is redundancy. Graduation year is redundant. The field is redundant, and this is not a normalized schema, right? That a better schema might have chosen to have the graduation year perhaps captured in the parent, right, as in enrollments and then graduation year 2009, as opposed to in each one of them, right? Because the redundancy might make it easier for me to introduce some inconsistency. What if this document had somebody who didn't graduate from 2009? Or I update one of these elements inadvertently and put it 2010, right? And then the query certainly might have some problems. Okay, but again, we don't know. We don't know if it's redundant. Only through the meaning of the field do we know it's redundant, right? Same thing with graduation. It says grade A, yes, right? What if all these all these students are awesome and they all got an A, even though all the values are A, right? The meaning of the attribute grade, right, doesn't mean that this is redundant, right? It means that they were all very good and they all have the same value. So it's not the value that should give us a clue on whether whether this field is redundant, is the meaning of the field. Make sense? Right? So you should never inspect the data, and the data should not let you know whether it's redundant or not. Right? It's the meaning of the field. So in XML, the enrollments here is the root element, which is grouping several children elements under it, which is all course taken. These elements, so the conceptually, enrollments is an element, right? And it could be represented as just in a tree where you have just a node element which contains many branches that branch out to many, several course taken instances, and the course taken instances might be leaves in this hierarchical tree. Now, the way it's represented in ASCII, right, is through what we call tags. We have an opening tag enrollments and a closing tag enrollments. Notice the slash at the closing tag. Yes, but conceptually, right, we can think of it as just a hierarchical tree, right, which has several roots. I mean, so it has one root and then has several nodes and branches that eventually end up with some leaves at the bottom. Okay. Right. So all these bracketed tags. Some of these tags are considered to be empty. Notice that enrollments has several subtags. So we say that the enrollment element is not empty; it has a body, right? And the body contains several other sub elements. But the course taken, notice that they do not contain any sub elements. So we say that they don't have a body, right? They are at the leaves of these inverted tree. Also notice that each one of these elements has additional fields in there, which we call attributes that have the format of name value pairs, name equal, and then colon, quotations of the actual value in there. The actual data type is interpreted by whoever parses this as either expecting an integer or string or whatnot or date. That is up to whoever declared the schema and whoever's parsing this. Whether we decide the data to be captured as attributes or captured as sub elements, that's a choice of deciding how the designing of the schema of the data, right? Same thing like we might decide in relational database whether something should be an attribute or a field of a table, or that field actually should be an entire class, an entire other table, right, that contains other fields. XML, all elements should be closed. So this is the closing tag of the enrollments there. Whereas the ones that don't have a body, they have a self-closing tag here, which is slash at the end. Right? That closes the tag. As I mentioned earlier, the choice, understanding that graduation year, if the meaning is that we are capturing all the students who have a particular graduation year, that gives us a clue that our representation was denormalized, right? And that we would want to normalize it by capturing that information at a higher level, right? So we might decide to bring it up to graduation year equal 2009, and this eliminates the redundancy, right? But there's only redundancy whenever, depending on the meaning of the field, right? Not because it has the same values over and over and over, right? So it's not the value that tells you the redundancy; it is the meaning of the field that tells you whether it's redundancy or not. Notice that grade makes sense to leave it at each one of the courses, so we're going to leave it there. Year taken, so even though we see different values, right, the meaning is also that it lives in the course taking is correct. So we might decide that another way of representing it might be using a more normalized or a more nested or a more hierarchical representation, and the two might be equivalent to each other, right? So let's consider here another data set here, which seems to be much more nested, right? So we have a root, the graduating students, and then presumably we have multiple instances of students. So student, and each student has a student name, graduation year, courses. Notice that we could have chosen, instead of the element S name, Ian, we could have instead chosen a student as an attribute called S name equal Ian. Yes? And they would be somewhat equivalent, right? Whether you choose one or the other is entirely your choice. It depends on whether that value of the S name is a fairly long piece of text or a piece of information, and that requires perhaps multiple lines of text to capture. But if it's something that is fairly concise, fairly small, then certainly the S name could have been instead represented as an attribute, right? But conceptually, they they're interchangeable, right? They mean the same thing as a way of capturing the information either in a much more concise fashion or much more verbose. So here we chose to not use attributes at all, right? Everything is being captured as elements, right? And that's perfectly fine, right? The parsers know how to parse either one, right, and tell you exactly what the values are for each one of them. So here we have S name instead of for the graduation year. Notice that we chose to have an element with the value as opposed to student could have an attribute called graduation year, right? We could have chosen that. But courses, notice that it cannot be an attribute, right? It has to be an element because it's going to contain several courses or several instances of courses, right? Again, the same choice when you're doing a table, whether it should be a field, right, or it should be an entirely different table, right? So here the choice of choosing courses containing multiple courses is almost the same choice of us deciding to do a split it up into multiple tables, right? Of choosing a nested list of elements, right, in XML is the equivalent of doing of doing a normalization, right, of splitting it up into multiple XML elements that are nested inside of each other. So here we have a list of courses. We have a course, and then the course has a title, a year taken, grade, and then presumably another course and another course and another course. And all these courses are presumably for that particular student. Yes? If we continue, we have here more courses for that student, and it closes here at the closing student tag. And presumably we would have another student underneath, right? We would have multiple students listed under here. Yes? And this is all well and good, but one of the things that you should be questioning is our choice of having capture the information of the course, as a subset of the student. Yes. What if there are two students that are taking the same course? Yes. Would you be representing that same course multiple times across multiple students? Right. That also is a consideration of whether we have redundant data. Right, that you have the course, course 5200 represented for Ian, and then the same course, represented for someone else, down below. Right, that's a clear indication that there is redundancy in the data that you're storing. Right, that instead of having captured the student just once, right, instead you're capturing the same information multiple times. That redundancy can lead into inconsistency. What if you want to, change the seats available in the course? Or the title of the course, or when it starts, you would have to iterate over all the instances of the course in multiple places, right? So again, whenever you're choosing the schema or you're designing the schema, you should always be looking for these examples of redundancies and how you might go about to reduce these these redundancies. So again, the same challenges that we saw in relational databases of normalization, first, second, third normal form for relational databases, applied as well in MongoDB, and also apply here as well in XML. Any data structure representation you choose to go with, you will always have those kinds of issues to resolve. Yes? All right, so the same concepts are applicable here as well. So here's a tree representation of the same information where we have at the top the root graduating students that contain a list of students, and then each student has information about that specific personal information about that student, and then a list of courses that has a list of multiple courses, right? And again, there's some issues here that we have calculus, Shakespeare, but notice that Shakespeare here is being captured twice. See that? It looks like Ian and Ben took the same course the same year, Shakespeare 2006. One of them got A minus, the other one C, but it's captured in two different places, the same course. So again, this might be an issue of redundancy. Now, if you have your application or some tool managing that redundancy, then it might not be an issue. Okay, very much like when we saw views or materialized views, where you can have triggers, and you can have that you're not managing the redundancy. You have triggers and procedures, right, that are managing the redundancy for you. So we could talk about perhaps good redundancy, right? So yes, I know the redundancy, as long as you have a managed way of managing that redundancy that allows you to have the redundancy but avoid inconsistency, then that's all in good, right? We know that oftentimes we deliberately denormalize not the base schema representation, but either a view or a materialized view. We look at a denormalized representation because it can provide performance boosts. Yes, and we might decide to go with the denormalized representation. But so as long as we manage that redundancy, redundancy can be good. Yes, if you know and you handle it correctly.